Uh, Understand that with vector data you have point farms and polygons, um, and uh, exactly what that means. Vectors, point lines, polygons, rasters, grid-based stuff. Know about georelational versus object-oriented, and why vector data is good. Understand what a TIN is. The TIN is it's a type of vector-based surface model, um, so it's not a raster. Digital elevation model, and a raster of elevation data. Understand that as with rasters, as your resolution gets smaller, the size of the data that your file gets increasingly larger, and that you really can only store one attribute. Have some idea what map scale is, distance on the map divided by distance on the ground, and that gives you some idea what it is. Know the difference between a small scale and a large scale map. Small scale means it's a small fraction, means it's 1 inch on the map is a very large number on the ground, where that gives you a very, very small number because it's a small fraction. So a small scale looks at a very large area, where a large scale map looks at a much smaller area. Understand about how modeling features, how things are supposed to behave the way that they do in the real world. This idea of logical consistency, of intersections being intersections and not underpasses or overpasses. Know what topology is and how it describes spatial relationships between features, things like coincident boundaries, as opposed to having gaps and overlaps. Logical consistency describes how well features mimic the real world. That's what we're talking about. Understand that topology is just a set of rules for how features interact with one another. Know the difference between a spaghetti model and a topological model. A spaghetti model doesn't have any topological rules. Each thing sort of acts on its own, doesn't care what anything else is doing. Topology models, features have various rules that describe how they interact with one another and that sort of stuff. Supports a lot of complex behavior like network analysis and that kind of stuff as well. As far as data quality, the thing you need to remember is in red, it's the third one down. Quality is defined as the fitness of a data set for a particular purpose. We talk about naming things, whether it's files or folders, it's the same kind of thing. Um, the rules are kind of broken down in two parts. First part being how you name them, and then the rules about how you name them. So how you name things is short, descriptive, and clear. Um, the rules for how you make a short, descriptive, and clear name are kind of simple. Never use spaces. Only use letters, numbers, and the underscore. Keep them short, 8 to 15 characters, and that'll sort of make it work for you. Let's see here. Never ever put spaces. Two types of coordinate systems: unprojected and projected. Unprojected based on the globe, projected planar coordinates or 2D sort of flat map coordinates. Um, Coordinate systems have their own data with them as far as the coordinate system information, and that's the kind of stuff that goes in there with that label, allows the software to read it so it can convert the numbers that are stored in the GIS. This is called the spatial reference. It's made up of a couple of things: the GCS of the datum, projection if you have one, the storage units, the domain, and the resolution. We talk about angular degrees and how we measure them. Looking at your longitude, you're simply measuring that angle um, uh, around the axis, and latitude is the up and down from the equator. Basically like that. Um, know that a GCS has certain properties, angular degrees, and where it starts and that kind of stuff. We don't use GCS data in GIS for a couple of reasons. One is because it's not real accurate, because you have to have super high precision, like multiple decimals, in order to get just a reasonable level of accuracy. And so a projected coordinate system works much better in that context. Need to know this whole process of The Earth isn't round, it's not a globe, it's more like an ellipsoid, which is kind of a sort of flattened globe. It has a major and minor axis, the major axis being the long, the minor axis being the short. Um, and that's sort of what we base our GCS calculations off of, is off of an ellipsoid. But what do you do with that? Well, that's where it gets a little interesting. We have to have something that we use for a zero level for elevation, something that sort of like we can think of as like mean sea level. That thing is the geoid. The geoid is this gravitationally defined surface layer. It's highly irregular, and you can't really map on it for squat. So it's just kind of it's just basic idea of what sea level would look like in most places on average. So what we have to do is create something called a datum, and in order to create a datum, you take that geoid in a specific ellipsoid, and a specific ellipsoid is one that you know the major and minor axis of, and then you look at the two centers of each of those, and you move the geoid around until it fits as good as possible to the ellipsoid. That is called a datum then. So how do we define a datum? We define it by the particular ellipsoid, major and minor axis, and the adjustment of fit, or how we move that center. Now when we do those two things together, then that gives us a GCS. If we want to have a projected coordinate system, then the thing you got to remember is every projected coordinate system is based off of a GCS, and every GCS is based off of a datum. So every projection that's out there has a datum, and so if you go from one datum to another, it can make things just off a little bit. As far as projections, they're just mathematical ways of converting that round space into a flat square space, and we do it a couple of different ways. Cylindrical, conical, conic, and azimuthal are the three primary types. We define these types by certain parameters, things like the central meridian, which is kind of that zero x equals 0 line on our flat map. We'll also use the reference latitude, which is also our y equals 0 line on our flat map. And then we have different ways that we sort of make the transition from round to flat. And typically two things come up. Like here we're looking at cylindrical projections. They tend to either be secant or tangent. Tangent has one standard parallel, secant has two. The thing about the standard parallels, on those standard parallels, there's almost no distortion. The further you get away from them, the more distortion you have. So if you have a secant projection with two standard parallels, depending on where you place those standard parallels, you can increase the accuracy of your map or of your projection. False easting and false northing doesn't do anything. It's just arbitrary arbitrary values that you add onto your map coordinates to make sure that for wherever you're working at, your study area, that you don't have any negative numbers. There's also different units. Remember things like angular degrees are in decimal degrees. Projected coordinate systems are typically in meters or feet. The extent is just the range of values that you have for these, like how far north, south, east, and west. When you look at the extent, you can get some idea because it shows you the decimal degrees where it's at on the globe. All map projections introduce distortion. We talked a great deal about this, but it's important to remember it. There's different types, and the different types distort different things. A good example is the Mercator projection and how it makes Iceland look, or not Iceland, Greenland, no, Iceland. It makes this large island here look the same size as Africa, and it's actually only 1/17 the size as Africa. Robinson's a good example of a compromise projection, and a compromise projection, unlike other projections that tend to preserve some things at the expense of others, a compromise projection distorts everything a little bit. So it tries to limit it so it doesn't distort anything too much, but it doesn't preserve anything either. So everything gets distorted just a little. Commonly used coordinate systems. GCS is really commonly used, but only for sharing data. The UTM system is used widely around the globe for doing stuff. State plane system is used here in the U.S. a lot, where each state has one or more zones that has specific types of projected coordinate systems that work well in that state. Let's talk a little bit about GCS, used to distribute data. Not good for maps or analysis because it has specific types of distortion and unit issues that you really can't work with. UTM system is one of the good ones. It's based on a transverse Mercator. So the Mercator is a cylindrical projection, but a transverse Mercator is a sideways cylinder. That allows you to rotate that cylinder so that tangent or secant point of contact from that cylinder moves as you rotate the cylinder. The idea with these zones are they're lined up so that point of contact is in the middle of the zone, so that everything within an individual zone is really pretty accurate and doesn't have much distortion. And where it's really useful is you can then move it around just by recentering that zone a little bit, moving a little to the east or a little to the west, and that will move your zone around. It works really well as long as whatever you're mapping fits inside the zone, inside a zone. State plane, multiple zones based off Phipps numbers. Use different techniques, use different datums, lots of different types of stuff in there. Here's a map of them. The three main types: cylindrical, conical, and azimuthal. We talked about that a few slides back briefly. What they preserve: cylindrical, direction and shape. Transverse is good for things that are oriented north-south. Conic data preserves area and distance. Works well for things that are east-west. Azimuthal, area and distance. Tends to work good for small areas or the poles. Projections for large scale maps. Remember, large map scale is looking at a small area. UTM state plane, perfectly awesome for that. Generally speaking, if you're in state plane or UTM and you're within a single zone, there is virtually no distortion to speak of. On-the-fly projection is the best and the worst thing of GIS. It takes data and displays it such that it looks like it's in the proper coordinate system. As long as it can read the coordinate system on some data, it will then temporarily reproject it so that it displays properly, but it doesn't actually change it. And so if you do analysis and things like that, it can get really, really wrong. To permanently project data, we use this tool to do that. It's called the project tool. When we use the project tool, it creates a new data file. That's how you can tell if you use the right tool. If you're trying to change a projection and you don't end up with a new file, then you use the wrong tool. So here's the project tool and how it works. What it does, georeference rasters. They've got coordinate system information already built into the raster, so it'll display properly. Resampling, you have a data set that maybe you need to reproject it, or you want to change the grid spacing or something like that. You have to take a new grid spacing or a new alignment and populate it with values from the old data. That's what resampling is. You make the new grid space, and now you have to populate it with information from the old one by sampling the old one. Three techniques: nearest neighbor, bilinear, and cubic convolution. Nearest neighbor is the simplest, the easiest, the least complicated. It looks at the center of the new cell, finds what's underneath of it, and that's the value it uses. Bilinear is a little more complicated. It looks at the 4 cell centers in the old data set that are closest to the cell center in the new data set, and then it uses a distance weighted algorithm to calculate it. Cubic convolution essentially does the same kind of math, but instead of 4 cells, it looks at 16. So that makes it slower. It also makes it, it tends to blur or smooth your data even more than what bilinear does. Nearest neighbor does the least amount of that smoothing. It preserves your original data the most. So there are some problems that come up with coordinate systems. It's important that you understand what they are and you know how to fix them. The two big ones are a missing coordinate system label or an incorrect label. Missing labels, you get a warning telling you it can be drawn but it can't be projected. When you have that, you've got to fix it. The way you fix it is you basically give it a label. And you do that with the define projection tool. And that's how you fix it. If something is labeled incorrectly, like it's labeled as in NAD 83 something and it's actually NAD 27 something, it'll be off by some offset. And so when you have something like that, on the fly projection, we'll project it, but it just doesn't show up in the right spot. So something like that, well, you know the label's wrong. So what do? You use that tool to give it a different label, and you pick from the most common options until you find the one that actually causes it to display properly. Once you've done that, you know you've now named it or labeled it correctly. And that's the tool and how you use it. Do not confuse these two tools. They do very different things. Project tool takes an existing data set that you want in a different projection, and it then makes a copy of it in the projection you want. Define projection is used when you have a data set that doesn't have a projection label or is labeled incorrectly, and it simply corrects or applies a label to that data set. Doesn't change anything. Don't mess these two up. Most of the time when there's problems, it's because of something with the coordinate system. When you're mapping stuff out, you got to think about the different things that go into how you map things like shape, size, thickness, line type, color, and pattern, and font, and how you can use these to display and share your information differently. Using color, understand the variations of color. When you're looking at how you symbolize maps, think about convention. Grass is green, water's blue. That makes sense. Think of the connotation. If you're mapping temperatures, hot is orange or warm is orange, whereas blue might be a cold. Also be aware that some people that look at your maps are colorblind and what that means, and think about that when you're designing and creating maps. Rainbow ramps work good for continuous surfaces. They're horrible for polygons. Black and white maps are really useful because they can be photocopied and printed without color, and people can see them. And people who are colorblind you don't have to worry about how they look to them because they're going to look the same. Limit your grayscales to 5 when you're doing black and white maps. Chloroplasts don't use multiple colors and stuff. That creates a problem. Tend to stick with one color. Classifying your data, there's different techniques. Jenks Natural Breaks is the default. How does it work? It creates a series of groupings. It measures the standard deviation of the groups, and then it averages the standard deviation across the groups and gets a value. Then it rearranges those groups and does it again and again and again until it finds that combination of classes to where if you took the standard deviation in each of these classes and averaged them together, that average across all the classes would be as low as possible. Equal interval is just equally spaced intervals. Defined intervals is like a set thing. Quantiles. Remember with quantiles, you stack your data up from low to high, and then you create your classes so that you have the same number of features in each class. So if you've got 100 data points, you got 4 classes, you go from your lowest to highest, your first 25, your second 25, your third 25, your last 25. Geometric interval, math function. Standard deviation, stats function. Normalizing classes, you do that by simply dividing by another field. For example, if you're looking at numbers of farms, it can be misleading. So maybe you look at farms per square mile, so you're looking at farm density. That's what normalizing is. Map design process is iterative. It sort of runs in a loop. You do each of these processes, and then once you do the process, you go, okay, I selected my data based on what I'm trying to do, my objective. I arranged it, I symbolized it, I looked at it, saw what it looked like, I made some edits and changes, and then I decide if I need more data in order to meet my objective, and you sort of just keep working around until you end up with a good map. Think of these questions. What's the purpose of the audience, medium, that kind of thing. Who's it for? How are you going to display it? Make your posters based on those things, or your maps rather. Cartographic generalization is how we take these complicated features that exist in the real world and sometimes in our data, and we sort of simplify them a little bit and we generalize them for the purposes of making our maps better maps. Not necessarily more accurate, but more useful. Selecting projections. Never, ever, 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 ever do anything in a GCS. Always work in projected coordinate systems. Pick one based on what you're trying to preserve. Unintended consequences, you make some choices about things, it really distorts stuff and makes some places that are really small look really, really big. Radical grids, if you're in a conic projection, a north arrow is not appropriate because it doesn't point north, because there's not one north, there's a bunch of norths. Radical grids follow the lines in the globe north to south, and so they're a more accurate representation of the direction of north in terms of a um, conic projection. Visual hierarchy is all about how you arrange stuff in a map, so the things that matter are the first things you notice. The things that jump after the things on top in front. How do you do it? By using these various things. Visual center, higher than the real center. Rule of thirds, don't put the stuff that matters right smack in the middle. Put it off to the sides, like where these dots are in this image. Alignment, you want to use things like columns and edges to keep things neatly aligned because it makes it look professional. Negative space is simply utilizing and distributing that space that's not used by your map on your map document. You want some, but you don't want too much. Top one's got too much, the bottom one looks pretty good. Balance things out. It's like putting flowers in your flower bed. You can't just shove them in anywhere. You got to try to put things in and see where they fit the best. When you make a map, review it, look at it, check your details, have other people look at it, print it off, all these things. Other people are really good reviewers because they'll see things that you didn't see and catch things that you didn't catch. 3-second test, about that. Modifiable area unit problem. This happens when you have arbitrary aggregation units like states or counties, and they influence stuff because they make you think, oh, this must be important because it's big or because it's dark. Or maybe the fact that the state's big means that when you're looking at things like the number of farms, it just looks like it's got a lot of farms. But it really has a lot of farms because it's a really big area. And so that's what modifiable area unit is. It's these artificial boundaries impacting the analysis. How do we minimize it? We normalize stuff. Um, Another type of the MAUP, or the modifiable area unit problem, is visual map. Visual MAUP occurs strictly because large polygons look important. Okay, modifiable area unit is because the large polygons, for example, make, or the position of the polygon, or where you decide the polygon starts and stops, that impacts the actual numbers. This impacts how you perceive it based on the size of things. And we reduce it by using different types of maps that don't rely on those things. Discrete versus continuous. Remember the pirate test. You're on the pirate boat. You're on the pirate boat. As you're walking the plank, it's boat, 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 till you step off the boat, and then you're in the ocean, ocean, ocean. That's discrete, clear, stop and starting points. Continuous is things like elevation. You have an elevation at the bottom of the hill, the top of the hill, the side of the hill, and the other side of the hill 2 miles down the road from the hill. You still have elevation. Thematic rasters versus image rasters. Know what raster pyramids are, that they increase the size a great deal, but they allow you to display rasters much more fast, much more quickly. Slicing, you look at the range of colors across the thing and you have to divide them out into the colors that you have available, so you have to sort of bend things together. Slicing looks at your minimum values and your maximum value and divides those out between your 256. Stretching basically takes these tails at the upper and lower end of your histogram and it sort of sticks them lower ones in one value and the higher ones in one value, and allows you to take that stuff in the middle and spread it out over more color ranges. It allows you to see more detail. Looks like this. Here you can see the different stretching effects and what they. Okay, so some rasters are actually almost like multiple rasters. It's something we call bands, and in some imagery, the colors that make up the color image are divided based on the wavelengths into different bands. So, for example, you might have a red, a blue, and a green band, or you might have some multispectral data that could have like 200 different bands. The actual image you see is generally represented by combining any combination of 3 of those bands. Typically, it's red, green, and blue. Um, but there are other combinations. And so that is one of those weird sort of situations where rasters can actually have um, more data than just the one value, because it's got that one value, but it's got it in three different sort of almost like sub-rasters, if you will. But that's kind of what bands are like. As far as tables, columns are fields, rows are records. Otherwise, it's pretty much just like a standard database table. Speaking of tables, you can have two types, standalone or attributes. Standalone is simply a table that you added into your workspace. An attribute table is something that's associated with either a shapefile, a raster, or a feature class. Different types of database management systems are out there. Flat file is the most common, the simplest, the most robust, the easiest one. It's the one that we typically use for just about everything. The downside is they're not real efficient for searching and things like that because they're just basically folders. Hierarchical systems are a little different. These are ones that have these parent-child relationships between folders and files and things, and they are designed with very specific queries in mind when they're set up, so that things are easier to access and they are more efficient when accessing those things that they're designed for. Relational databases store the multiple things. They're very flexible. They're open-ended. This is the type that we typically use in GIS applications. One of the things we do in GIS is run queries and simply put a query as something. It's just a command that's entered using a special language that extracts certain records from a table based on the conditions you outline. The language we typically do that with is something called SQL or SQL, Structured Query Language. It allows you to write these um, phrases that dictate the conditions that you're looking for in the data set. They can be a pain because they're nearly always case sensitive, and so spelling errors, capitalized, not capitalized, that kind of stuff can really make it difficult to get good results. Here's some examples. Select by attributes is another means of querying your data. It's basically a graphic user interface sort of version of a query, whereas you can ask the GUI what it is you want to do, create a new selection, select from an existing selection, add to an existing selection, etc. And then it has various elements there that allow you to functionally click and select out um, a query statement that then selects based on what you're asking. Once you do a selection, whether it's select by attributes or select by locations or some other type of query, once you select a subset of your data in your attribute table, it'll look kind of like this. On the left, you can see that you have the selected and the unselected, and if you go to the one on the right, how in that one we've selected the other option, which is just the selected features. And then there's always to remember the clear selected features. It is important to do that after you do analysis if you want to work on the whole data set, not just the things you have selected. Joining and relating tables. Joining tables, you have to have a common field. Common field doesn't have to have a common name. It just has to have common data. So it could say FIPS number on one, and it could say FIPS on the other. As long as the two columns, the two fields, both have the same FIPS type data, then you can join those together because they should match up. So if it's a 5-digit FIPS number in both of them, it doesn't matter what it's called. You can line those up and then join the second data set to the first. Joins are temporary. You have to make them permanent if you want them to be permanent. They have to have a common field. It treats two tables as one. When you don't use them anymore, you can get rid of them. Rules of joining boils down to this. You can only join one thing with one thing. Or one thing with many things, but you can't join many things to one thing because it doesn't work because you only got one box. So if you're trying to take information from like the state of Washington and add it to all these cities in Washington, you can do that because it's still going Washington one spot here to Washington one spot there. There's just multiple spots over here where it's joining to. Whereas if you were to try to join the stuff here on the left in the bottom to the stuff on the right, you'd have multiple things going to one thing. You can't do that without summarizing the data and joining it that way. So in general, it's all about taking one thing to one thing, one thing to one thing, one thing to one thing, one thing to one thing. Relates are basically very, very similar to a join, except it doesn't actually join things. It just allows you to select that in one table, and then it selects the corresponding information in another. Fields, fields are just the columns in the attributes tables. No more than 13 characters, only letters and numbers. Got to start with integer versus float. Integers are whole numbers, real numbers, not negative numbers. Floating point uses a scientific notation kind of format with a mantissa to calculate out the values you're looking for. Precision is either single or double. It has to do with the number of digits in the mantissa. The more digits in the mantissa, the more exact and the more precise your answer can be. As far as storage goes, lots of different types, ASCII, integer versus float, all kinds of things that go into it, but I'm not going to ask you any questions about that. Different types of fields that you can have in an attribute table. These are important to know. Big one is short, is basically plus or minus 32,000. Long is plus or minus 1.4 billion, or 2.14 billion. Float is 8 significant digits. Double float is 16 significant digits. Geometry, okay, whenever you have a geodatabase and you have a feature class in it and you generate a polygon or a line or what have you, there's some measures of geometry that get created. Some of these are automatically created and maintained in feature classes in a geodatabase. Specifically, shape underscore area and shape underscore length are the automatic area and length fields that are created in feature classes in a geodatabase, and they are updated automatically. Every other instance where you have a field that identifies area or length in any fashion, in any format of any data, it will not be updated automatically. So assume all area and length measurements are incorrect and need to be updated. Shape files, nothing gets updated automatically. Queries extract certain records from a mapper table. We already talked about that. Aspatial and spatial. Aspatial queries are all parcels with a greater value than 100,000. Think of that as like select by attributes. Spatial queries are all the ones that lie within a floodplain that has to do with the spatial position of something relative to another data set. So here's an example, elevation, pick one over a certain range, and that's what it gets identified. SQL, structured query language, you already talked about it. Order of operations, some things are important, some things are commutative, some are not. You need to know which ones are which. And remember, if you have to change the order of operations, you got to use parentheses. Spatial queries. Three conditions that we look at with spatial queries. The basic spatial relationships. Intersection. Does this touch or cross that? Containment. Is this inside of that? Proximity. Is this close to that? Spatial queries can employ a number of operators. It's just a list of some of them. Target and source. I'm not going to ask you questions about that. It's too confusing for an exam. Intersection operators, a bunch of different ones. Here are some examples. Containment, more examples. Types of contain, more examples. Clementini. Alessio Clementini and some other folks thought of this special condition where the outside border of a polygon is also not part of the polygon. It's weird. It shows up once in a while. If you ever have a situation where you need to not have included the boundary of the polygon, then you want to remember Alessio Clementini and his special set of operations. More proximity examples. Again, additional examples. More examples. Scale and accuracy. What is perfectly accurate at one scale will be horribly inaccurate at another. Notice the image below. The blue line that was drawn for the river at one scale looks fine. At another scale, you can clearly see it doesn't line up with the river in the image. And you might say, well, what difference does that make? Well, it could make a lot of difference. It could change whether something is in or out of an area. Topology, we've talked about it before, we'll talk about it again. It's all about things having sets of rules that make them behave a certain way to one another, to follow some degree of logical consistency and act like they do in the real world. For example, two counties, Bennett and Shannon, they are side by side. They have a boundary that is coincident. And so if you have a coincident boundary, then these two counties have one boundary, and that one boundary is the boundary for each. In this example, each of the two areas, Bennett County and Shannon County, have their own boundaries, and they're not identical. This violates the basic topological constraints here. It should be the same line. Instead, we have gaps and overlaps, and that's not good. Same way with South Dakota and Nebraska state line. That should also be the bottom line of the Shannon County, and it is. It should also be the bottom line of the Pine Ridge Indian Reservation, and it's not. The Indian Reservation doesn't line up with those other data sets, and it should. Extraction functions. These are very similar to select by location, but they work a little different because they split things up. First one's clip. When you think of clip, think of the cookie. You have some tool, it acts very much, it uses some polygon or some feature very much like a cookie cutter, and it gives you the cookie, which is the area in the first data set that's defined by the area of the second. The counterpart of that is the erase function. It's the same but exactly opposite. Again, cookie dough, cookie cutter, but instead of giving you the cookie in the end, you get the dough minus the cookie. Clip and erase. Clip keeps the features inside the boundary. Erase keeps the features outside the boundary. Just examples. Length and area. When you use a clip tool like that, it shortens the length of some things. Okay? When you do that and you modify things, those length and area calculations are going to be wrong unless they are shape underscore length and shape underscore area in a feature class in a geodatabase. Those will update automatically. In every other instance, those measurements will now be wrong. You have to recalculate that geometry. Spatial queries is simply like any other query, but instead of searching for specifics in the attributes, you're basing it on the physical locations of things. And so you can select from current selections and add to it just like you would with an attribute query. Once you've made a selection, regardless of whether it's attributes or spatial processes like proximity, once something is selected, you can export that data. You can make layer files. I don't like doing that. I prefer you guys do it this way. Go to data, then go down to export data. Make a new data set, add the new data set into your table of contents, and do whatever you need to do with it. Spatial join conditions. Join two tables based on a common spatial field, one feature inside another, one closest to another. The examples that they use are these cities and airports. If you join the airports to the city, then each city will have its closest airport identified, and then that airport's information will be joined with the city. So the information from one airport is joined to multiple cities. Whereas if you do it the other way around and you join the city information to the airports, then for each individual airport, there's a handful of cities that are closest to it. You can't join those multiple things to that one thing, so you have to summarize that information. They talk about inside joins and outside joins. You can read through these and make sure you're square on. Okay, we're going to talk a little bit about cardinality. Cardinality is typically considered to be like north, south, east, and west, but that's not the kind of cardinality that we're referring to. We're talking about one-to-one, one-to-many, many-to-one, many-to-many. That's the cardinality that we worry about in GIS. So when we have here, the example is destinations and airports. So you can join the airport information to each destination, or you have to summarize the destinations to the airport because you don't maintain a one-to-one cardinality. One airport to multiple different destinations, and each destination still gets an input from one airport, so that's a one-to-one. So one-to-one works good. Now, whether something's a many-to-one or a one-to-many gets confusing, so I'm not going to get into that. Just another example showing what that means. And how summarize joins, you take all the stuff in the circle and then calculate up the averages and apply it to the airport. Spatial cardinality, again, not going to get into the many to many, one to many, and many to ones because that'll get confusing. Point to points are easy when they're distance. It's simply find the closest one. The only issue is you got to make sure everything's in the same projection because that can change what's closest to what. This little diagram helps you understand inside joins versus distance joins. In other words, schools that are in a county is inside, whereas hotels closest to an amusement park is a distance. And then if it's summarized, like you have multiple schools that you're joining to a single county, or multiple attractions that you're joining spatial data to a single hotel, those would be summarized, whereas if it was the other way around, it would just be the simples. Feature types, every join involves two geometry types. When you're joining two things together spatially, it's either points to points, polygons to lines, or lines to points, something. Every combination offers two possible types, join or summarize. Don't pay any attention to that slide. Don't pay any attention to that slide either. Here's an important one. When you do these joins and you look at this stuff, here we have some data in a GCS, and we're looking at this stuff here, and you see this distance comes up these weird numbers. It's because it's in a GCS, and so it's not in meters, it's not in feet. It's in some kind of angular degree measurement, which is really impossible to calculate into an actual measurement because it changes all over the globe, and so you don't want to do that. So never, ever, 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 ever do any spatial analysis in a GCS. Distance joins, again, can't do it with a GCS. Get everything projected, get everything in the same coordinate system, make sure the coordinate system is appropriate for where you're at, and then you can do it. Same thing. Map overlays. Multiple data sets, you put one over top of the other. The cool thing about that is it forces a one-to-one cardinality. Essentially, when you do map overlays as opposed to a spatial join, it forces the data sets to create new features. Everywhere something overlaps, it splits. And then the new features have a complete and perfect one-to-one cardinality for both the original data sets. And so you don't have to worry about summarizing stuff. So why would we overlay? Well, that was the big reason, was what I was talking about in the last slide. Spatial joins, on the other hand, are awesome for some things, but they're not awesome for other things. They allow you to do things like gather statistics on road lengths and stuff like that, but the problem is when things cross over boundaries. That's where the overlay functions work better. So map overlay will split those things instead of just doing the spatial join. Lines and polygons use intersect to associate with land use categories with the road. So you got a road, you got land use, use intersect, it then figures it out. Types of overlays, point and polygon, line and polygon, polygon and polygon. This just kind of explains what each of them are. You can read up on it if you're interested. If you think it's something you need to know, or if you look at a question in the exam and say, oh, I don't remember that, here's where you'd look. All right, let's see what we got there. Polygon and polygon stuff. What are the steps to combine everything spatially, combine the attributes, bring everything together? You get the new thing. So you have data set 1, data set 2. Data set 3 is all the possible polygon shapes that could be combined by having those two combined, so that everything in the final output has a one-to-one cardinality with some aspect of both of those data sets, like you see here with the example. Overlay, we talk about two big types here, union and intersect. Union keeps and combines everything. Intersect only keeps the stuff that's common to both features. So with intersect, you got some sort of an object, you got some sort of a target, you put them together, you get everything from the targets that's inside the thing that you're using to define your area. Union, it's the exact opposite. You get everything that's in either one. And so overlays look kind of like this. Intersect keeps common areas, union keeps everything. So here you got the green box and you got the yellow squiggly. And when you combine them, the intersect is whatever's in the yellow squiggly. It's also inside the lime green box, and so it's the purple stuff you see in the top. With union, everything that's in either data set comes out as part of the union. More examples. More examples. What happens when you intersect different geometry types? Well, you can get all kinds of crazy stuff. When you intersect polygons, you can get a polygon. You can also get a line, because you just want the line of where the two polygons are, or the points where the two polygons intersect one another. And so you can select different geometries from your intersect. Okay, but the dimensions of the data that you select has to be the same or lower than your least complicated data set. So if you got two polygons, you can end up with polygons, lines, or points. If you had a line and a polygon, you could end up with lines or points. If you had points in polygons, you could only end up with points. Does that make sense? I think so. All right, so output dimension must be less than or the same as the lowest input dimension. Here we have lines intersecting can give you lines or points, which is kind of what I was just saying. Another example, we're intersecting a circle and the lines, and so the only thing we can get is lines, which is lines that are inside the circle, or we can get points where the circle intersects the lines as that. But we can't get polygons because we have a data set, an input here that's of a lower order. So let's look at all the overlay operations together here. We got clip, erase, intersect, and union. Clip and erase does not join attributes. It's just a simple means of reducing the area of something. With the clip, think cookie cutter. You clip something, you're left with the shape. If you erase something, it removes the shape from the other data set. Whereas with intersect and union, these are overlay functions that join attributes. Intersect gives you all the data that's common to both data sets. Union gives you all the data in both data sets plus the attributes. Area and length calculations. Clip and erase obviously will make features not be the same length that they were or the same area that they were. It changes the dimensions and geometries of features. When you do that, all the measurements that you have as far as areas and lengths are potentially going to be incorrect. Now, if you're dealing with a geodatabase, specifically a feature class in a geodatabase, and you have shape underscore length or shape underscore area, those two fields in a feature class in a geodatabase are updated automatically. Every other scenario that you can come up with, a shape file instead of a feature class, nothing updates automatically. A length field called length doesn't update automatically even if it's in a feature class in the geodatabase. Only those two update automatically. Everything else doesn't. So my advice, anytime you clip, anytime you erase, anytime you project, anytime you do anything that potentially changes anything, no matter how small you think it might be, recalculate your geometry. Dissolving, you got a bunch of polygons on the left. This could be from any number of things, and you ultimately want to combine all the B's, all the C's, all the F's into single features or multi-part features. Well, that's where the dissolving tool comes in. You simply select the field that you want to dissolve by, and it does that. Now, one problem, it doesn't really keep the rest of your attributes. It just gives you the one that you wanted and dissolves everything else away and just focuses on that one. It eliminates all of the attributes in the table except the one you dissolve by. Buffering. Buffering is simply creating a polygon at a set distance around an object. Append. Append places features from one feature class into an existing feature class of the same type. Unlike union, it does not attempt to split or change features. If they overlap, they simply overlap, and you'll have two of them. So when you use tools like append, you've got to be a little bit careful. Append is essentially just shoving more data into another data set, which if it's all new data and there's no overlap, is not so much a bad thing. Merge. Merge combines two feature classes into a new feature class. So one takes data, append takes data and adds it into an existing one. Merge takes two inputs and gives you a new output. Talk a little bit about efficient overlay. Overlays can be time and memory intensive. In other words, it will make your computer grunt and squeal like a little pig. And so what do? Well, you can either sit there and watch the smoke come out of the side of your desktop, watch your laptop bounce around like well, I can't think of anything offhand that bounces at all. So if you don't want your computer to have lots of difficulty and you want to try to make things easier, use efficient overlay. So you want to do things that minimizes the number of these things, like dissolve, so that you don't have 3,000 polygons, you only got 200. Um, Trim down your area, use clips and things like that to remove stuff that you know ain't going to go. Slivers are tiny polygons that are produced when you do overlay functions um, and other types of geoprocessing where you have these tiny little bits of things where stuff that should line up didn't line up exactly. They can create anywhere from mild annoyances to shutting everything down to not being a problem at all. We fix slivers by setting some of the controls, tolerances, and things like that to eliminate that sort of stuff. Again, shape underscore area, shape underscore length in a geodatabase and a feature class are updated automatically. Nothing else is. Everything else is always wrong. Assume everything is wrong. Just go ahead and recalculate all those. And these two to be safe. Because what if you're wrong? What if it's not a feature class? What if it's not in the geodatabase? What if you made a mistake? Well, if you update the geometry, at least your calculation will be right. Pixels versus cells, they're synonymous with the same thing. They're basically tiny little squares in a grid and a raster. Pixel depth refers to the data storage structure of those. The thing that you need to focus on and remember is the range of values that you can get per certain pixels, like 11-bit, 16, 24, looking at the range of values 0 to 255, 0 to 65,000, 0 to 16 million. You can look in your raster properties and learn a lot about your data simply by scrolling. Um, you can also find rasters like this one here that happens to be a bill, which is it's a type of satellite photo, but it happens to be a multi-band raster. And so while it is a single raster, if you open and expand it, you'll see that it has 7 different bands inside, each band representing a different range of electromagnetic energy. But at the end of the day, each of these bands kind of act like their own little raster, but when you display the image like you see there on the right, it's by selecting 3 of those bands to display together to represent red, green, and blue. And then that's what you get. Why do you use rasters? Really good for certain kinds of data. Certain kinds of data already comes in it. It works really good for some maps. The precision is not as good. The files are honking huge, and you can't store multiple attributes. So it's not perfect, but it is a really simple, robust. I'm going to do one thing, do it perfect, and then do the next one thing and try to do it perfect, and then do the next one thing and do it perfect kind of approach to GIS. Raster resolution is measured by the cell size dimensions. If you have a raster that has a 30 by 30 meter cell spacing, that is your raster resolution. Raster analysis uses cell-by-cell functions where you do a calculation. For example, 3 data sets. You find the same cell location in each data set, and then you do whatever you do between them, whether it's adding them up, multiplying, dividing, what have you. Resampling is a common technique that we have to use in GIS. Where we have inputs that don't line up. Maybe we have one grid spacing for one data set, one grid spacing for another data set. We try to combine those. The only way we can do that is to resample so that we get a new grid spacing that works. This also happens whenever we project data or change the projections. A lot of times that means we have to go through the same process. But when we go through that process in that context, it's more automated. It's not a separate function, it's just an option that you select. Oftentimes when resampling is necessary for a tool, um, unless you specify, it's just going to use its default settings, and so you have to watch, because if you don't make a decision how you want to do that, it's going to make a decision for you. So here are the 3 common resampling techniques that you absolutely have to know. Nearest neighbor, bilinear, cubic convolution. Nearest neighbor, simplest, looks at the new cell center, finds the value under it on the old cell. That's the one it uses to replace to populate the new one. Bilinear looks at the cell centers of the old cells. The 4 that are closest to the center of the new cell, uses those on the distance weighted algorithm to calculate the new value. Cubic convolution, same process as bilinear. Instead of 4 cells, looks at 16. Cubic convolution is slower. It creates more of a smoothing effect than bilinear. Bilinear is smoother than nearest neighbor. Nearest neighbor preserves your data the most. I just said that there earlier. It automatically resamples for a lot of stuff. If you don't tell it how you want it done, it's just going to do it the way it wants. Map algebra, raster 1 plus raster 2 equals output 3. pretty simple in raster. In vector, it's a little more complicated, but it's actually, instead of looking like pancakes stacked like this kind of map algebra is, when you start doing this in vector data, it's more like doing calculations across columns and rows because you're doing it in attribute tables. Here's an example of map algebra. We have a precipitation layer that's in centimeters. We're Americans. We don't use the metric system. The metric system is for commies. So what do? Well, we convert it to English standard measures in inches. And so there's a calculation there. Centimeters divided by 2.54 equals inches. How do you do that? Use raster calculator. Put in your data set 98 precip centimeters. Divide by 2.54. You get a new output. It's the one on the right. That's precipitation in inches. You can also use it for cut fill. Data set 1, data set 2, one minus the other. Boom. You can see where stuff is taller, where stuff is smaller, i.e. cut and fill. You can also use it to model other equations, things like this. Here's some kind of a calculation to measure how prone something is to landslides or what have you. You can also use it to do complex environmental type models. Here we have a Borlein layer for elevation where we have it must be to a certain range. If it's not, we're not going to use it. We have slope has to be under a certain amount, we're not going to use it. We have crown cover has to be greater than a certain amount, we're not going to use it. We combine all these three Borlein layers in a certain way, and we get outputs that meet all the criteria or don't meet all the criteria. When you do it this way, things that meet the criteria become a value of 1. A value of 1 is synonymous with yes or true. Whereas a value of 0 means, nah, it's not going to work. We can't do that. It's no good. It's a 0. It's a lie. Drawbacks of Borlein overlays, it is just plain out simple. Simple was good a lot. Simple can be problematic because a lot of things that are simply true or false in reality just aren't going to be simply true or false. Borlein overlays don't support that differentiation, that gradation of suitability. It doesn't allow for maybe. It doesn't allow you to compare one location to another. It just simply says, will it work here? Yes or no. And if your answer is not the same as yes or no, then Borlein's not really a good way to go about it. Then you would want to do something like an index. Typically, we do index models as weighted overlays. Weighted overlays are simply linear combinations where we assign weights to each input, rank them, or however you want to do it. There's a lot of different ways. Ultimately, to calculate some sort of an indexed value, an indexed value is just a numeric output that gives us a particular score for a particular cell in a raster or a particular polygon. And that number that it generates, we'll say, is 12. What does a value of 12 mean? Absolutely nothing. It means it's better than 11. It's not as good as the 13. It allows you to compare one location to another location to infer relative to what you're thinking about in modeling, is this a better or worse location? It doesn't speak to is this a good location or a bad location. It simply tells you how it relates to the surrounding areas. And those numbers are not transferable to other locations. You can't run the model here, run it somewhere else, compare from one side to the other. It doesn't work that way. The values that you get are only useful in the context of the model that you ran to get that value at the location you ran it. Some examples: landfill suitability. Have your various layers ranked, weighed. Weighed is the relative importance. You get Borlein outputs. You combine them together. In this case, they added each of the inputs together. And so if you have 3 inputs and you add them all together, and your scores are between 1 and 3, 3 would be the best location and 1 would be the worst location. And so based on that and these inputs, you see that the locations that have a 3 are the best locations. All right, more about raster calculators, how we do a lot of this stuff. It's in map algebra. Other functions that we do, analysis that we do, reclassification, surface functions like slope and aspect, distance functions, density, interpolation, neighborhoods, and zonals are all important. Reclassify, take a raster, it's got some values, you want it differently, you can convert it, for example, to ones and zeros. You can take an elevation layer, pick a range like you do for your class project of, like, say, 900 feet. Everything below 900 feet becomes zeros, everything above becomes 1. You make it into a Boolean data set using the reclassify tool. Surface analysis, you can do things like take your digital elevation model and calculate slope, the direction, its rise over run times percent times 100 gives you the percent slope, which is the change in elevation, and slope is just the greatest change in elevation. Here's how slope works. You can measure it as degrees too, but we're going to probably talk about it mostly in percent. Aspect is simply the direction of the steepest slope. Hillshade is simply a shadow based on a set sun source location. View sheds are what you can see from a given location. Cut and fill, we talked about that. Interpolation, taking the known data that you have and filling in the unknown data in between. So here we got some sample points. What we're really looking for is to figure out what the data is everywhere else. We can use an interpolation to fill in the blanks, if you will. Same thing you got to remember, interpolation values are not the truth. They're not real, okay? They're calculated based on a set number of sample points, and the data that you generate is only as good as that. And so if your data has a lot of variability, like actual elevation values, and you only have a handful of points to go by, it's not going to give you a good look. As you can see here, the elevation values that we interpolate from just these handful of summits is nothing like the actual elevation that exists in the digital elevation model. So what are some of the methods we use? Inverse distance weighted splines, kriging, and trend. Density functions look the same, but they're really different. It's all about how frequently something occurs over a given area. Two types, simple and kernel. Read about them if you want to know more. Neighborhoods. When you calculate neighborhood statistics like zonal statistics, that kind of stuff, neighborhoods are set ranges you can do this with to calculate, for example, the minimum value. You identify the shape like a window. It looks inside the window at the values in the raster and it picks whatever statistic you ask for. Windows can move in one or two ways. They can move in blocks or they can move focally. Blocks means they move by a certain size chunk and they don't overlap, and everything in the block gets the same response. So you identify an example here, block A, that first group of, what is it, 5 by 5. It would then do whatever statistic you asked, and whatever the answer was, it would put that answer in every single cell inside block A. And then it would move on to the next block, which would be another 5 by 5 right beside it, block B, and do the same thing. A focal function is similar, but instead of moving one block at a time, it literally just moves over one cell. And so it's calculating and processing that for one cell. And so you would do that for every cell in the grid. For example, here processing on the right in cell A, it takes all the stuff in the red box, uses that number to calculate your answer. The answer goes in that single cell right there for A. Then it goes to the next cell beside it, and that's the one we'd use the stuff in the green box to process that value, and it goes in there B. When you calculate B, it doesn't use the new value for A. It runs off all the old until it creates a brand new data set full of these processed values. So what happens? What does it do? What does this make your data look like? Here we have an original land cover data set. If we apply a 4x4 focal majority, so focal means it's moving one cell at a time, and for each cell it looks at a 4x4 block. It makes the stuff on the left look like the stuff in the middle. If we use a block function where it moves that 4x4 and then populates that entire 4x4 with whatever the value is to the next one, you see it looks more like the one on the right. All right, so let's pick back up here pretty quick. Neighborhood focal functions are simply just what you see here. I want you to find the window in the target cell, and then it calculates up. And here you can see you're looking at an average and what that would do to the output. The effect of this, using things like a focal mean, where you look across that region and average the values, is it smooths the data out. You can see in the image on the right how the raster is much more blurry looking. That's where fine detail becomes more spread out, bled in, however you want to look at it, or smooth, whatever the terminology best resonates with you. This is sort of another way of looking at it. Here we have a slope area, looking at high slopes and low slopes, and we're trying to make it less complex and simpler by using a 5 by 5 majority filter. What that really means is you look at a 5 by 5 grid space and it analyzes all the cells in that grid space and says, okay, what's the most common answer? And whatever that is, that's what it applies to that center cell. And by running that over multiple times, you start to erase these tiny little slivers and subsections and things, and you end up with a more solid looking polygon type setup like you would see here. It's actually not a polygon, it's a raster. But you would run something like this before you would convert it to a polygon. Zonal functions are very similar, but they're also very different. They also use these kind of areas just like a block or a focal function, but instead what you use is some other data set that defines the zones. Typically it's like a bunch of polygons that you're using to define a zone, and then in that zone you're calculating a statistic from a raster data set. So here we have zones, there's the polygons. Zonal statistics, we're here in an example, watersheds, trying to figure out what's the average slope in a watershed. Takes the slope of the watershed, calculates from it, gives you the output. There you go. You can do it for lines as well, and it works for points. When you're doing editing, there's some things you got to remember, like dangles, undershots, and overshoots, where things are supposed to stop on one another and they don't. You want to avoid improper intersections. Is it an intersection? Is it an overpass? Or is it an underpass? These are the things you got to fix, and that's where, with proper editing techniques and stuff, you can make it so that they're not a problem. You can avoid gaps by using things like autocomplete and cut polygon tools. You can also set up topology rules in data sets so that when you create features, you can then test to make sure that you don't have gaps and overlaps. More on improper intersections, pseudonodes, correct topology, and all that. So we've looked at a couple examples there of the different types of topology, how severely are problems with topology. Some you can't tell. Some are a little difficult to deal with. Some stop stuff in their tracks, and others get you sued. You have to understand that sometimes you'll have things that look like they're topological issues, but they're not. It actually might be an underpass, an overpass. It might be a cul-de-sac. These are the things you have to look out for. Again, go back to the ideological consistency. It is the fundamental question of topology, is how well features mimic relationships in the real world. Does it behave in the GIS the way it's supposed to behave, or the way it behaves in the real world? How do we maintain it? In a spaghetti model, God help us, we don't. Spaghetti models don't store topology. They include shape files and things like that, but there's no means of testing stuff. The only thing that you've got to give you any version of consistency is some of the tools like snapping and auto-complete polygons, stuff like that. But it basically places the entire onus upon the GIS technician or analyst to correctly create adequate topology without the use of topological rules. Now, if you have a topological model, that's an entirely different ball of wax. They are set up with rules in place and interactions between features so that you can test to see if it maintains logical consistency, if things that are supposed to coincide do. And once you set that up, it allows you to go in and fix these things. There's a version of topology that's pretty useful called map topology. It allows you to edit multiple features like shapefiles using some sort of like a weak temporary topology. It's a topological association we call map topology. It allows features that have a shared boundary to be edited at the same time. So you got two polygons, they have a similar or coincident boundary. You move the boundary for one polygon, it moves the polygon boundary for the other one. Cluster tolerance is another tool we use to create some better topologically consistent product, where we try to click on something and we leave a gap because we don't quite get close enough. We adjust those tolerances so that it makes those things connect like they're supposed to. Problem is you set the settings too big and it doesn't help, and if you set it too small, it doesn't help, and you set it too big, it just automatically starts snapping things to everywhere. Metadata is data about your data. Data quality is defined as the fitness of a data set for a particular use. Don't forget that. Types of geodatabases. Personal file SDE. Personal, small, Windows-based, single user, small group. files are stored in folders. Um, they're pretty useful. SDE are awesome if you have access to them. They utilize commercial software and have some really unique features like version editing. Planar topology is basically rules that we have set up in place, topologically speaking, to deal with the relationships and interactions between layers or elements like overlaps and gaps so that you can't have them. Network topology is all about the network connectivity within the data set. It's a more advanced level of topology. It's all about things like which direction traffic can flow, how fast it can flow, whether there's stops and intersections and that sort of stuff, whether something goes up or down, how big a pipe is, how much water flows, anything like that that has to deal with a connected transmission, if you will, could fall under the realm of network topology. Version editing allows you to do what ifs, so you can just play with stuff and see what happens. You don't like it, hit a couple buttons, and you just roll back to the way it was before you started screwing around with everything. Schema is a document that we utilize in some GIS that basically explains all the structure of everything in a geodatabase. All the feature classes, all the feature data sets, all the parameters and fields, and how everything's laid out and put together, and everything about it.